Continuing our work on magnetism and chapter 27 on magnetic fields, the next section that we want to look at and topic is 27.4. This is a discussion of Gauss's law for magnetism. This is a very simple section, but it is also one, it looks deceivingly simple, but actually it is very powerful. We will derive here, or acquire, discuss, one of Maxwell's four equations. This whole first part of this semester, is devoted to understanding the four Maxwell's equations. So obviously this is something of great importance. We have to use some vector calculus. That's even one step beyond regular calculus, but I'm going to try to make this intuitive so that you understand what we're doing. It's very similar to when we used Gauss's law for electricity. And you remember there, we looked at something called the electric flux. And we defined a flux there. If we had a charge Q, and it was giving off an electric field going out in different directions like so, if we had a surface that went around here, we could talk about the total amount of flux that from the electric field that crossed. And that flux was equal to, if we look at every little square, how much electric field came out of each square times the area of that square. So it was the electric field times an infinitesimal area, which we could write as dA, or we often use d sigma for that. And it's the dot product. It's the dot product because the surface is pointing in the perpendicular to the surface points in the same direction as the electric field. And then we had to add that up over the whole surface, which in calculus means we integrate. And so this is a rather advanced concept to integrate over a closed surface, over this whole surface. And we found out there that the total flux through any system due to the electric field was equal to the charge inside divided by epsilon naught. Well, now we're looking at magnetic flux. And we got an entirely different picture here. It's not nearly as hard. The flux, if we have, say, a north pole here and a south pole here for a magnet, and if we look at some kind of surface around here that contains this magnet, then as you know, the magnetic field points in the same direction as a magnet would point. So it points away from here, goes out here, comes back, goes all the way through. That's important to realize. That magnetic field line goes all the way through. It doesn't have a beginning and it doesn't have an end. So you can't wrap the surface around the North Pole or the South Pole. If you do, no matter how close you get, there's a line that goes out of the magnetic field, B, and a line that comes in of the magnetic field, B. So what goes in always comes out, so the total flux is always zero. And that's the thing we learned. This is electric. The magnetic flux through a closed surface is the same thing. It's the integral of B dot d sigma over the entire surface, as I've written here, over a closed surface, but it's always zero. And this is just as important as this other law up here, which is Gauss's law for electricity. So this is Gauss's law here for electricity and here for magnetism. And these are two of the foundational equations that constitute Maxwell's four equations. And what this means is this is equivalent to saying that through any closed surface there's no flux. That's the same as saying, or equivalent to, there are no magnetic monopoles. In other words, there's no pole like a North Pole. If there were, we could put a surface around it and it would give off flux that would go through the surface, adding up to something like it did with the charge. It also means there are no sources and no sinks, no separate north and south poles, another way of saying it. No sources and no sinks. It also says that the magnetic field lines always close back on themselves in closed loops. Every magnetic field line does not have a beginning or an end, but is closed like a snake eating its tail. And that's basically what we needed to learn right here, was this other Gauss's law, the Gauss's law for magnetism, which tells us that there are no north poles floating around out there. Now, it's important to realize that they're not precluded from our theories in physics. We simply have never found one. And all of our equations of electricity and magnetism are based on the fact that none exist. But it is known how to alter them if we ever find one, some exotic particle that just has a north pole with it. And someday, something like that may be found. Later on, we'll talk about that and some work that Dirac did, another famous physicist. Again, these are two Maxwell's equations, Gauss's law for electricity and Gauss's law for magnetism.